Good day, everyone. Today, we will talk about the Barber paradox. The Barber paradox is a famous logical paradox introduced by the mathematician and philosopher Bertrand Russell. It demonstrates a problem of self reference and sets that leads to contradictions. There is a barber who is said to follow this rule. The barber shaves all those and only those who do not shave themselves. The question is, does the barber shave himself? If the barber shaves himself, then according to the rule, he must not shave himself because he only shaves those who do not shave themselves. Number two, if the barber does not shave himself, then by the rule, he must shave himself because he shaves everyone who does not shave themselves. No matter how you answer the question, it leads to a logical contradiction. If he shaves himself, then he doesn't shave himself. If he doesn't shave himself, then he does shave himself. This paradox arises because of self reference and the attempt to define a set, the people who are shaved by the barber, in a way that includes and excludes itself at the same time. Here are the syntax that we're gonna use to really understand what we are doing later on. Colon equal means is this is how we write a function where the left side is the head, name and variables, and the body on the right side, the logical expression. I'll elaborate more when we go there. EX means existential quantifier. All means universal quantifier. Prime means negation for Boolean algebra formula. Exclamation point means negation for tau formula. End symbol means end logical operator. Pipe symbol means or logical operator. F means false. T means true. And N means normalization. Here I wrote down some of the things that we will see later on. There is a barber who is said to follow this rule. The barber shaves all those and only those who do not shave themselves. The question is, does the barber shave himself? Later on, you will see this one where this is the title, as we recall a while ago, colon equals, where on the left side is the name of the function, and also this one are the variables used. And on the right side is the head, is the body, where this is the logical expression. So this is a bit very simple, but yet very deep. So x is equal to y prime. So this means that x is the barber that shaves y, if and only if y do not shave themselves. So what I understand is that x is the barber and y is the customer who do not shave themselves. Now the paradox begins with this. Again, let's recall colon equals, where the left side is the name of the function and the variable, and the right side is the logical expression. In the left side, this is the paradox, and we introduce a new variable b. On the right side is the logical expression, where we can say, or we can see, a while ago I showed you EX means existential quantifier, and all means universal quantifier. This is a very deep subject that we will talk about in the future coming lessons. But right now, let's stick to this. By the way, all of these formulas and logical expression was shared by a community member, Logix. Thank you, Logix, for sharing this. Let's continue. So here it says that there exists a barber, B, such that for all X, B shaves X, if and only if X don't shave themselves. This is my interpretation. So B is the barber, hypothetical, and X is also the barber. So let's clarify things out. Let's go to the Tao language REPL to perform these logical expression. Okay, here, so um, I will use Tmux, terminal multiplexer, to have two windows. And then from here, let's type in Control B and then percent. So on the left side would be the demo, and then um, the right side would be the analysis, our analysis. Okay, so let's go to Control B left to change the panel. So here I'll also teach you how to download Logic's demo. Okay, so what we're gonna do. So let's go to CD tao lang demos. And then from here I want to download here. So from here let's go git clone and then the address https slash github.com tau mo ro slash tau lang dash demo dot git. Okay, so before I didn't check that I don't have the internet connection. That's why I failed to do this, but just check, make sure that you have the internet connection so you can download it. Okay, so let's see if we have it. So let's type there. So we have here, um, so let's go to this one. Barber, copy, paste. Okay. So here, let's again, so this one we will use this one. So what we're gonna do is we will use that slash run dot sh and then the name of the demo, barber underscore demo underscore 2 dot tau. Okay, so let's start. Hello, let's have more fun with the Tao language. What's the barber paradox? It's a puzzle about a barber who shaves everyone who doesn't shave themselves. The question is, who shaves the barber? First, we define a more explicit form of the barber function. Barber x comma y colon equals x equals to y prime. And once we enter this, this will be the result. So let's see. Let's do it by ourselves. So here, we have to go to cd tao lang build release. tau. Sorry. Okay. So here let's clear this one out. So here this is the barber x comma y. This would be the head, okay? Where this is the name of the formula, and these are the variables used, x and y, closed by the open and closed parentheses. And then colon equals. So this is the left side. The right side would be the head. The head is the logical expressions. So this is x equals to y prime. Okay. Okay. So here we see that um, we typed in x is equals to y prime, and tau gave us a different thing. It looks different, but as we analyze, so here I this is the this is the original formula that we typed, right? And then from here, um, I wrote the truth table, as you can see, and the point why I want to show this one is to show you that um, this is what we input, right? And then after we entered it on the tau REPL, tau evaluate the formula and gave this formula. Okay, and right now we want to see whether this two formula will give the same outcome. Okay, so this is also I want to grab the opportunity to practice our analysis using the and or not logical connectors. So again, this is the blue arrow. This shows that we what where we are right now in our analysis. And the first thing that we're gonna do is to write down the values, the all the possible combinations of two variables x, y. So here the barber x, y, and then this is the equation. Um, yeah, I wrote I put the color of the variables, so I mean the same colors, so it's easier for us to see to differentiate the different variables. Okay. So let's begin. So first here is we know that this is 0 0 1 1, and this is 0 sorry, 0 1 0 1. Okay. After this, we will also do this one here. Okay. So um, in our previous lectures, we learned the function or the logical operator not. This means that it's the opposite. So if this is false, then not x is true. If it is true, not x is false. So this is just the opposite. Okay. So here we focus our attention um, on y. So here, right? So let's highlight this one. So here, the opposite of 0 is 1. The opposite of 1 is 0. The opposite of 0 is 1, and 0. Okay, that's it. And then after that, what does this mean? So this means that um, x is equals to y prime. So if x is this is x, so we will highlight this one. Let's focus our attention to x and also focus our attention to y prime. Okay. So means to say, if they are equal, if x and y prime are equal, then we will have a 1. If they are not equal, then it's 0. So here, so x and y. So x is 0, y prime is 1. Are they equal? No. If they're not equal, so it's 0. It's false. Here, are they equal? 0, 0? Yes, so this is true. Are they equal? 1, 1? Yes. Are they equal? 1, 0? 0. That's it. So we see that the value here is 0, 1, 1, 0. Okay. Now, let's see this expression. Again, let's just copy this one to make it faster. This is the all the possible combinations. Okay, so here x prime, so we focus our attention to x. So that would be 0 becomes 1, 0 becomes 1, 1 becomes 0, and 1 becomes 0. That's it. Let's now focus to our attention to y. So this becomes y prime, so this becomes the opposite of this. So that would be, this becomes 1, this becomes 0, this becomes 1, and this becomes 0. Yeah. Okay. Now, let's end x and y. So x and y variables, we have to focus on this one. And then here, let's recall the end function. This is the end function. The end function shows that output will only have a true statement if both the two inputs are true. Else, everything will be false. So here, so 0, 0, 1, 0, 1, 0, 0. And this is the only one. That is 1. It's 1, 1, 1. Done. Okay. Now here, so we will focus x prime and y prime. So we'll focus this variables. Okay. So 1, 1 is 1. 1, 0 is 0. 0, 1 is 0. And 0, 0 is 0. Done. Let's continue. So here, this expression is x prime and y prime, this one. And we will OR it with xy, so this one. Okay. So here it's OR. Let's recall the function of or the logical operator OR. So either one of the one of the input is true will be true. Okay. So here, since there is 0, 1, so there is one input is true, so this is true. And here 0, 0, 0, 0, 0, 0. 1, 0 is 1. Done. Okay. Now here, um, x prime and y prime, or x and y equals to 0. So we have the attention here. Okay, let's focus our attention here. So here, it says here, if the expression is true, then it will become 0. Okay. So here, is the expression true? 1? Yes, so this is 0. Here, is the expression true? Is 0. So that would be the opposite. It's not. Send and this one. And this is true, so it becomes 0. So here we can see that the formula here is the same as formula here. Look at the results. They have the same. Here 0, 1, 1, 0. And here is 0, 1, 1, 0. They're the same. Yeah. Okay. So it only shows that um, Barber x comma y colon equals x is equal to y prime is the same as this expression. Okay. So here we can see that Barber x comma y, x is equals to y prime. Okay, and we have analyzed this one a while ago. The result is 0, 1, 1, 0. And here, after tau evaluated the logical expression, it gave us this one. So we analyzed also using the truth table, and this is also the same. Okay, so let's just do this one. Okay, so that's it. So, and then let's continue the demo. Okay, so here this means y is shaved by the barber x if and only if y doesn't shave themselves. Now we describe the whole paradox. Paradox B colon equals there exist so ex means existential existential quantification, and all is universal quantification. Okay, so let's try this one here. So paradox B, this is the title, and then the variable used is B, and then exist B such that all x barber if and only if B x okay are the same. Okay, so yeah, let's continue. This statement says there exists a barber B such that for all x, B shaves x if and only if x doesn't shave themselves. Great. We are ready to start the questions now. Number one, can such a barber exist? Okay. So normalization and paradox B. So tau gives F or false. So let's try it ourselves. So here it's first let's write here the question one is can such a barber exist? Okay. So here um I would like to show you this one that um this expression, okay, we can use the truth table to analyze and know the results here, right? Okay. So, but before that, before this one, let's try to normalize this one to really make sure that what we see on the Excel, I mean, what we see, what we analyzed a while ago is same as in the tau REPL. So, let's normalize to barber. So here, okay, and then this is n. Okay, I'll show you also our analysis. So here, 0, 0 would give us x is 0 and y is 0 will give us 0. Same, x is 0, y is 0 will give us 0. So this would be x is 0, y is 0 would give us 0. So instead of 0, it's f is false. Okay. Next, um, here x is 0, y is 1 is 1. X is 0, y is 1 is 1. So this is 0, 1. This is true. Okay. Next, x is 1, y is 0 is 1. X is 1, y is 0 is 1. So this is x is 1, y is 0 is 1. Okay. And last, okay, x is 1, y is 1 is 0. Same, x is 1, y is 1 is 0. So 1, 1, 0, 1, 1. So this should be false. Okay. Okay. Okay, I want to add something here. So in the previous lesson that we learned, okay, so we have the formula f1 open parenthesis x comma y comma z close parenthesis colon equals, and then x or y and z. Okay, and then when we normalize this one, okay, and when we change the value of x, y, and z to either ones and zero, okay, so tau will give the result of 1, okay. But here on our Barber paradox demo, okay, we write like this. So also, this is the name of the function formula, and then these are the variables colon equals, and then x equals y prime. Okay, and then when we normalize this and we also change the value of x and y, 1 and 0, instead of 1, it is true or t. So why is this so? Okay, so this is because of the syntax. Okay, so the syntax, okay, so I was also confused while I was doing this one, and I was asking myself, I don't have any idea uh, why when I normalize this formula, it gives me 1, while when I normalize this formula, it gives me t. Okay, and thank you for PTTKK. Thank you for giving me the advice. One member of our TownNet and Agorist developer chat. He gave me the idea that yeah, um, Tao treat the formula differently. Okay, so this is about the syntax. Okay, so there is the Tao grammar. Okay, let's see in GitHub. Okay, in the github.com/idni/taolang. Okay, we can find here um the Tau grammar. Okay, so when you say Tau grammar, this is when Tau see this kind of format. Okay, grammar. It treat is it as such. So this one. Okay, so here in our second formula, the barber. Okay, so there is an equal here, right? You see the equal sign here. So when you have a logical expression with an equal sign, okay, so this means tau treat this one as a tau formula. So here we can see term equals term. So this means to say tau will treat this one as a tau formula, and tau will give the result of either true or false. Okay, whereas um, whereas for the constant, let me search this one. Okay, so for the constant, so here, uh, comparing this to the first formula, this one, you see, for this one, see, it's only this is only a term, okay? This is separated by a and uh, or, right? So in that case, in that case, tau will give a result of either ones or zero. And this first formula is a Boolean function, while the second formula, tau, see this as a tau formula. Okay, again, the first formula is a Boolean function, and the second formula is the tau um, here. Um, yes, tau formula. Okay, so I hope it's clear. Boolean function, it will give you either ones and zeros, and tau formula will give you either true or false. So it's clear, and so just give us um, okay. So what we showed here that using the truth table we can analyze the results here. But here in this quantifiers like existential quantifier and universal quantifier, the domain might be infinite, so it's not practical to use the truth table. So okay, so here tau really is very powerful because it can um, give us the result when we run this one. Okay, so here, so let's write n normalization paradox. So before that, let's write the question to make it clear. So question one is, can such a barber exist? So this question is we want to know. So wait, sorry again. So we have to write the um, number sign. So to this means it's a comment. So it will not Tau will not run this one. It means Tau knows that this will be a comment, and will just ignore this one. Okay. So here, um, question one: can such a barber exist? So we logics wrote n paradox p. Okay. So here, um, um, it's like we 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 said a while ago that um, in this expression, x is equal to y with there is no quantifiers. When there is no quantifiers, we can use the truth table to analyze the result, right? The domain may be the domain is finite, but for when you have in your logical expression, when you have existential and universal quantifiers, the domain is infinite. So means to say, how would you analyze that one? Okay, so it only wants. This is only my idea. I might be wrong, but what I guess is that um, we want to know whether um, look at this one. Barber, this expression, right? X is equals to y prime, right? This one. So we wrote down all the possible combinations of x and y, right? And then all the possible combination, it gave us one in this combination, right? It, this expression becomes true when you have the combination of x that is 0 1, and another combination is x is 1 0. Okay, when your x is 0 1, and when your when your variables x and y is 0 1, and also when your variables x and y is 1 and 0, it will give you a true statement. This is true, else it is false. Okay, so in when when dealing with this equation, this logical expression with the extension existential and universal quantifiers, it's like the question is, will there be a 1 here, the result? Okay, will there be a combination of these? Okay, will there be a combination of these such that um, there is a combination that it will give you a result that is true? Okay, so that is it. Okay, so tau is very powerful because uh, as we have said, when you have the universal and existential quantifiers, your domain is infinite, right? So let me give. I'm just learning together. Together we learn. So if you have any question or maybe I'm wrong, you can tell me what is it. So I'm learning also. So together we learn. Okay. Together we learn. Okay. So here we will normalize the paradox B. So this one. And it says here that when we enter, it's false. Means to say, in all possible combinations of this one, okay, it will not give you a true statement. Never. I mean, uh, there's no combination of such to give you such. Okay, but here there is a combination, right? A while ago I have shown you. There's a combination. There are two combinations. This one, row two, okay, will give you a result of one, and row three also will give you a result of one here. With this combination, it will give you this result one. But here, okay, in the paradox B, sorry, paradox B, this equation, logical formula, okay, with all the infinite domains, it will not give you a combination that is true. Okay, so that's it. That's what I understand and interpret. And if I'm wrong, just let me know. Thank you so much for that. Anyway, Control B. So Tau evaluated the paradox to false F, which means it determined that no such barber can exist. Okay, so it's quite amazing to for Tau to know that I. It's quite amazing for Tau to know that in an infinite domain, um, um, there is no such combination that will exist. Okay, so anyway, that's my interpretation. So here, question two: is it impossible for this barber to exist? Okay. Uh, let's see here. So Q2, question two: is it impossible for this barber to exist? Okay. So here we logics wrote n and then as exclamation point. As we know, exclamation point is a negation. It is the opposite, paradox B. Okay. So here, so we if you put the opposite here, right, it should be true because it's the opposite of false. It's true, right? So in the question one, we ask, well, can such a barber exist? So means to say, are there combinations, any combination in that infinite domain? Are there possible combinations that will give you the result to be true? And there is none. Okay. Here in question two, it says, is it impossible for the barber X to exist? Means to say that is it really true that like um, will it never will it never have a combination that will give you the true statement? Okay, is it impossible for this barber to exist? And this is true. Okay, so why do we want to know this one? Okay, later I will show you. It's a nice learning actually. So here, let's go back here. Um, okay. Tao evaluated the negation to true, confirming that it's impossible for such a barber to exist. Okay. We learned what we learned. Okay. So I will type here. Okay. Defining the barber's action as two variable function, barber x comma y. Okay. So I will elaborate more about this. So two variable functions. So we have two variable, the variable x and the variable y. Okay. We define the barber's action. So this is the barber's action, right? Okay. And using existential quantification, so this is the existential quantification, the EX. As we have said a while ago, EX is existential quantification. Okay. B followed by universal quantification, all X. So all when in the syntax of Tao language REPL, when you write all, it means universal quantification. When you write X, it's existential quantification. So here, using existential quantification followed by universal quantification, correctly captured the essence of the paradox. Okay, Tao was able to prove that the paradox leads to a contradiction by evaluating it to false. Okay. Tao confirmed the impossibility of the paradox by evaluating its negation to true. So, as we see here, right, we get the false, right? And when we negate it with the sign of exclamation point, Tao gives us the true uh, result. Okay. Interpretation of paradox B, evaluating to false F. So what does this mean? Okay. So in question one, can such a barber exist? And Tao says no, it's false. It means that the Tao has determined that no barber can satisfy the condition B shaves X if and only B shaves X if and only if X doesn't shave themselves for all X. In logical terms, Tao has proven that the statement there exists a barber who shaves all and only those who do not shave themselves is false. This aligns with our understanding of the paradox such a barber cannot logically exist. So interpretation of exclamation point paradox B, evaluating true T. Okay, so this confirms that the negation of the paradox is true. Okay, so when you negate the false, it becomes true. Okay, in other words, it's true that there does not exist a barber who shaves all and only those who do not shave themselves. This double checks our first result, providing additional confidence in Tao's handling of the paradox. Okay, so here, okay, so Tao was able to handle the paradox. Okay, when you negate something, okay, it's obviously when we negate the false, it should be true. Okay, but in a domain that is infinite, right? So it's very amazing how Tao did that one. Okay, handled that kind of paradox. Anyway, so Tao's handling of quantifiers. Again, when you say quantifiers, these are the existential quantifiers used with x, ex, and universal quantifiers, all or all. Tao's handling of quantifiers, the correct Tao correctly interpreted and processed both existential and universal quantifiers, demonstrating its ability to handle complex logical structures. Okay, so Tao really can handle this one. Okay, the existential and universal quantifiers. Okay, Tao's processing of Boolean functions. This one. Okay, Tao correctly interpreted the Barber x y function, translating it into Boolean algebra. This shows Tao's capability to work with user-defined functions and translate them into its internal logical representation. Okay? Consistency of results. The fact that paradox B evaluated to false and its negation to true shows the internal consistency of Tao's logical processing. This consistency is crucial for a logical system dealing with complex paradoxes. That's it. So I have taught you how to open, how to download this one, and also you can try it yourself, okay, to really see the power of Tao language. Thank you so much for your time. If you have any questions, suggestions, or clarifications, just write in the comments below, or you can join our Tao Telegram group channel. And also, you can write on the, or you can post your questions on the Tao forum. Okay. Thank you so much and have a good day. Bye.